Hi everyone, I'm Supravat Ghoshal, and in this talk, I'll be talking about the biased homogeneous Arlene problem. Uh, so, the problem that we study is a very interesting variant of the Max Arlene problem. Now, the Max Arlene problem, of course, is one of the most classical problems in theoretical computer science, and it's one of the most natural computational problems one could come up with. So it's basically the following problem. Um, we are given a system of R variable linear equations over F2, and the objective is to find a F2 valued assignment to these variables which satisfies the maximum number of equations. Now, this is a classical problem in theoretical computer science, and there have been tons of works which have studied this from the point of view of algorithms, hardness, approximation algorithms, hardness of approximation, and so on. Also, apart from being a natural and fundamental problem on its own right, it's also one of these problems which comes up naturally in the context of constructions of several objects which are frequently used in complexity theory, such as error correcting codes, pseudo-random generators, probabilistically checkable proofs, among others. And finally, the setting when R is 2, the IT2 setting exactly expresses the Boolean unigames problem, which is of course central to Coates unigames conjecture. And there have been many works which have also studied this from this point of view. And in this work, we focus on the setting where R is at least 3, that is, the IT is at least 3. Now, okay, what do we know about the complexity of this problem? Firstly, it's of course an instance of Max Arlene is of course a system of linear equations. So if it is satisfiable, then we know how to solve it in polynomial time using Gaussian elimination. But then what happens when it's not satisfiable? Then let's consider this following naive thing to do, which is let's guess a assignment for the variables uniformly at random. That is, for every variable in the system, we set them to probability we set them to 0 with probability half and 1 with probability half independently. Now, how good is this naive algorithm? Well, if you pick an equation and that equation basically consists of variables which have been set to 0 or 1 uniformly at random. So the expression corresponding to that equation will be 0 with probability half and 1 with probability half. So every equation will have a chance of probability half of getting satisfied. So overall, this implies that this is a half approximation algorithm. But then one can ask, well, this was a naive thing to do. Maybe we could be more clever and we could maybe use more sophisticated techniques and design an algorithm which gives us a much better than half approximation. This was ruled out by Hastad, who showed that we can't really do better than half approximation efficiently. So it's actually NP hard to get half plus epsilon approximation for any constant epsilon greater than 0. So the naive random guessing thing was really one of the best things to do in terms of solving this problem efficiently. And as hardness of approximation people like to do, they label this problem as being approximation resistant. That is, it's hard to get anything better than the naive approximation one can get by random guessing. Now, a slightly changed version, but closely related problem is the homogeneous balanced Max Arlene problem. Here, we are given a system of homogeneous R variable equations. So of course, because it's homogeneous, it's always satisfiable. You can always use the all zeros assignment to get assignment which satisfies all the equations. So the twist here is in the objective, which says that we want to find a balanced assignment for these variables which satisfies the maximum fraction of equations. Here, balance just means that we want to look at assignments which have the same number of zeros and same number of ones in the assignment. Again, what can we do about solving this problem? Let's go back to our fallback random naive thing to do, which is this random guessing algorithm, right? So note that because the algorithm itself sets every variable to 0 or 1 with probability half, with high probability, most of its guesses are almost balanced up to lower order terms. Also, as we saw, this is a half approximation algorithm. So overall, this is a feasible algorithm for the homogeneous balanced max Artin problem. Again, one can ask is, okay, we have a naive random guessing algorithm which can give us half approximation, but can we possibly do better efficiently? This was ruled out by Holman and Court, who showed that, again, you can't really do better than half approximation in polynomial time, but under a stronger assumption, which is that NP is not, unless this wouldn't happen unless NP is contained in sub-exponential d time. And this was later on strengthened to show that there is actually no quasi-polynomial time algorithm which can do better than half approximation. This was done by Haster and Manokaran, who used short codes instead of long codes in their reduction. Now, this work, the problem we study is a generalization of the balance setting. So we study the p-biased homogeneous Artin problem, which is as follows. So here again, we are given a system of R variable homogeneous equations, but then the objective is to find a p-biased assignment which will satisfy the maximum fraction of constraints. Here, by a p-biased assignment, we mean that it's an assignment which has p fraction of variables set to 1. And in particular, when p is half, this exactly recovers the balance setting that we just saw. Now, again, what can we do to solve this problem? Right. So again, we can go back and design a appropriate variant of the random guessing process, which is the p-biased random guessing process. So here, we set every variable in the system to 1 with probability p and 0 with probability 1 minus p independently. Again, due to the fact that every variable is set to 1 with probability p, this almost always creates outputs assignments which are p-biased up to smaller order terms. So this is a feasible algorithm. But then one can ask if this p-biased random guessing is really the best thing to do. So the main question that we study in this work is that is p-biased guessing algorithm is really the best algorithm for the p-biased homogeneous Artin problem for every value of p. In other words, we are asking if the p-biased homogeneous Artin problem approximation resistant for every value of p in 0 to 1. And this really is the main question that we study in this work. Now, before we can start to answer this question, let's actually figure out what the approximation factor is for p-biased guessing. So let's do exactly that. Let's fix a R variable homogeneous equation, and let's compute what is the probability with which p-biased guessing will satisfy that equation. So using standard techniques where these are standard steps where we first arithmetize the probability of an equation getting satisfied. This is done by translating the variables from 0, 1 to plus minus 1. And then we'll use the independence of the guessing process to show that this exactly comes out to be half plus half times 1 minus 2p raised to the r. So this is the probability with which any one equation gets satisfied. And therefore, the total fraction of constraints that can get satisfied in expectation is exactly, again, half plus half times 1 minus 2p raised to the r, which means that this exactly is the approximation factor of p-biased random guessing. Now, in our results, what we will do is we will compare how good is this approximation factor in various regimes of P and R. So to begin with, let's look at the setting where P is less than half, that is P is in 0 to half range. So there, our first result is the following. We show that for any P in 0 to half and for any R greater than equal to 3, it is there is no polynomial time algorithm which can do better than half plus half times 1 minus 2p raised to the r minus 2 approximation, unless np is contained in sub-exponential d time. Now, as we just saw, on the other hand, p-biased random guessing gives us a half plus half times 1 minus 2p raised to the r approximation algorithm, which put together means that we have matching bounds for almost matching bounds when r is large. So in particular, this says that p-biased random guessing, it has to be at least nearly optimal, if not optimal, in this range when when r is large. But then what happens when p is greater than half? This is where something interesting happens. Firstly, we show that no matter what p and r is, there is a constant factor approximation algorithm for the problem, which is independent of p and r. So formally, for any p in 0 to 1 and for any r, there is a half times 1 minus e to the minus 2 approximation algorithm for this problem. On the other hand, note that if you look at the approximation factor of p-biased guessing, then when r is odd and p is reaching 1, then the approximation factor is actually going to 0. So what does that tell us? So we can now combine the two things and make a couple of remarks. Firstly, it's obvious that p-biased random guessing is strictly suboptimal when r is odd and p is reaching 1. So the algorithm from theorem 2 strictly dominates the approximation factor of p-biased guessing. So that means that there are ranges of p and r where the p-biased homogeneous R-line problem is not approximation resistant. Also, as we'll see before, the algorithm for theorem 2 is based on a linear programming relaxation and then rounding it appropriately. So, which is it's actually quite different from random guessing. So that seems to tell us that there is a range of parameters in which the algebraic complexity of the problem is dominant, and that is why random guessing is optimal. And then there is another range of parameters where the combinatorial hardness, complexity of the problem is more dominant, and we need a more combinatorial algorithm, which can beat the random guessing algorithm. Now, finally, to complete the picture, we also show that this P and R independent bound is actually tight. So there is a R and a P depending on R, such that the P-biased homogeneous R-line problem is NP hard to approximate beyond half times 1 minus e to the minus 2 approximation factor, assuming the unique games conjecture. So we actually get matching P and R independent upper and lower bounds for the problem, assuming the unique games conjecture. So those are, in summary, our results. So in the rest of this talk, what I will do is I'll try to provide some intuition for why random guessing can be bad when R is odd. And this intuition will actually help us design an algorithm which will beat random guessing eventually. So in order to do that, it's useful to think of for the rest of the talk, it will be useful to think of a p-biased homogeneous Arlen instance as a CSP. So constraints will be represented, equations will be represented by edges. So an HE will represent the XOR constraint on the variables which are supported on the variables which are part of that edge. Now, a crucial but simple observation here is the following: that let's take an assignment and an equation, and suppose this assignment satisfies that equation. Then it must be that if R is odd, then it must be that at least one of the variables in the equation must be set to 0. This is because when R is odd, the all ones assignment does not satisfy that equation. So in other words, we like to think of it as follows: that suppose there is a global assignment to all the variables, and this assignment satisfies one edge. Then it must be that the 0 set of the assignment must be hitting that edge. Now, this observation immediately suggests ways to construct examples where random guessing can be far from optimal. For example, let's consider the following the instance. So here, this instance consists of 1 minus 3p prime fraction of vertices are isolated in this instance. That means that the variables corresponding to these vertices do not participate in any equation, and there are the remaining 3p prime n vertices form a perfect matching of arity, where each edge is of arity 3. And here we can think of p prime as being 1 minus p, where p is the bias of the homogeneous Arlen instance. Now, what can we say about this instance? The first observation is that this instance has a p-biased assignment which satisfies all the constraints. For example, what we can do is we can set one variable in each equation to be 0, and every other variable can be set to 1. This is clearly a p-biased assignment. But then every equation here will have even number of ones, and therefore will be satisfied by this assignment. So that just tells us that this is an assignment which satisfies all the equations. But then what does random guessing do? In random guessing, what will happen is it will spread the zeros quite uniformly throughout the set of variables. And what will happen is the 0 set of the assignment will hit at roughly 1 minus p fraction of the constraints. And therefore, that will also imply, using the previous observation, that this will also almost always satisfy close to 1 minus p fraction of constraints. And this is bad when p is reaching 1. So what's the takeaway from here? The moral of the story is that when the budget of zeros is small, we need to be more careful about how we assign the zeros. In particular, it would be more useful to try to find a small set of vertices which hits as many constraints as possible. And this is precisely how we will design our algorithm. So here's a rough sketch of the algorithm which will beat random guessing. So as a first step, we are going to find a set of relative size 1 minus 2p, which hits the maximum fraction of edges. How do we do that? So we write a coverage type linear program relaxation, and then we solve it and we do independent rounding on it using the same analysis as the analysis of a max coverage linear programming relaxation. We will be able to give this guarantee that this will hit at least a constant fraction of the optimal number of edges that were satisfied in the optimal solution. And in the next step, what we do is once we have found this set S, we assign uniformly random variable values to the variables in S, and we set every other variable outside the S to 1. Overall, with a little bit of work, we can show that this will yield a p-biased assignment up to smaller order terms and will satisfy half into 1 minus e to the minus 2 fraction of constraints. Now, I'll conclude this talk by quickly going through the techniques that are used for the other hardness results that we have in this work. So firstly, we have the PR dependent hardness. For that, we use Holman and Coates mixing label cover as the starting point. So the mixing label cover has a very nice one-sided mixing properties that can be used to control the averages of the local long code tables using the average of the global long code table. And the inner verifier is, of course, a dictatorship test. So this test is a generalization of Hostad's 3-bit test, but this is a generalization to the p-bias setting. So this particular test is the most technically involved component of this work, and it could be of use in other applications as well. On the other hand, we also have the PR independent hardness. For that, so the hardness is unique games hardness. So the reduction is from a hypergraph variant of unique games. The dictatorship test is based on a pairwise independent distribution that is supported on even weight strings. And because unique games does not have good mixing properties, we have to be more careful during the soundness analysis. So we have to use the concavity of the soundness expression to control the averages of the local long code tables using the average of the global long code table. Now, I'll conclude my talk with a couple of three nice questions which are open-ended and are I feel like they could be fruitful areas for future work. So the first immediate open question is the following: that so we in this work we get algorithms and hardness which are almost matching in maybe some regimes of parameters. So it would be good to the immediate open question here is to find optimal algorithms and hardness for p-biased homogeneous RDN for every range of p and r. The next broad thread is that here we attempt to study the notion of biased approximation resistance. So typically, approximation resistance is usually studied with respect to uniformly random guessing. But here in this work, we study the optimality of random guessing where the guessing is not uniform. It's p-biased, and this could be this is again could be a broad area of work. We can come up with a systematic notion of identifying problems which are approximation resistant for some range of p's, and then the question of what are optimal algorithm for the for such problems when they are not approximation resistant in some other range of parameters. So all of these questions become relevant. And finally, another interesting question is this surprising thing that we still do not have half plus epsilon NP hardness for balanced homogeneous R3-link. This is primarily because there are some serious technical bottlenecks which have to be overcome towards designing outer verifiers which have really good mixing properties. But then, even if we couldn't get NP hardness, one could still try to see if we can get half plus epsilon NP hardness under stronger assumptions, such as Unicam's conjecture or even small set expansion hypothesis. So this is all that I had to say in this talk. I hope to see you all in the conference and the poster session. Thank you for listening.